All right, let me begin with a word of prayer as I get up here. Then I will explain the many questions you have about the curious grading of the math battle. Dearly Father, we thank you for this day. I thank you for these students. Just pray that you'd help us to use this day wisely, just to try to settle any remaining questions before the test tomorrow, and just pray you help the students to just fill in any gaps that still remain in their understanding of integration, and just to do their best, Lord, for your glory. In your name I pray, Lord Jesus. Amen. So the grading is, let me explain. All right, so what I did was I started grading like problem by problem. So if you're in team 1, you have the good fortune of knowing that it's problem 1, problem 2, problem 3, problem 4, problem 6, problem 7. That's the meaning of the numbered columns. All right, so I graded the first 7 problems, well, first up through problem 7, somewhat carefully. I looked at them. And then, so it's out of 60 decipoints. So then the number you either have, between 20 if there's like kind of something there, but it's not really that close. 40 if it's like 2/3 done. 60 if it looks pretty much on point and it looks correct. 50 if it's like, kind of close, but anyway. 5 if there's like a sign of life, but not much else. And then, so anyway, that's roughly speaking you have 60 decipoints per problem. So those 7 are like that. Now, I will say problem 5, everybody got 60 points for. I'll explain why that is. So that's what I did for the first 60. And then what I did at that point was realized I didn't want to stay up all night grading. So then I decided to just count the rest of the problems that had looked like you had a serious attempt for. And so the number to the right, so I've got like a plus 360, plus 660, plus 420, plus 420, plus 360, plus 120, plus 540, plus 420, plus 300, plus 480. It depends on which group you're in, but that's like 60 points per problem. I'm just give you the benefit of the doubt and suppose it's right, which of course is false. Like, I know they're wrong, but whatever. So,
thank you for the confidence.
Well, there exists a subset of correct, well-deserving problems in there that I should have given the 60 points for. And the rest, I'm sorry, I gave you what you did not deserve. Anyway, all that said, then I added the points together, and then I also added 60 because the 60 for problem 5 for everybody, that has to be added. So that's why I have the boxed number, and then the other number I think is that plus 60. And then what I did is I looked at the numbers that I had and I said, oh, well, that's too low. So then I doubled it. So then I multiplied your one group had 525, so I doubled it to 1050 and 1050 decipoints, which is 10.5 points. So the circled number is the actual grade that will go into Math Battle 1. But anyway, the long story short of it is you just try your hardest to do the most problems that you can correctly, and then you'll earn the most points in the next math battle, right? So that's kind of it. Let's see here. I'll tell you who won. In terms of raw points, looks like I think 720 was the highest number of raw points. That was group number 2. So if you guys would like to come to my office to pick up the air horn for a week, you're welcome to. If you want. If you don't, it's okay. But just remember as you use the air horn about campus that it didn't come from me. Do it in convo. Okay, so listen. So let me just quickly go through the math battle. I don't have a complete solution, but I'll post what I have. I don't usually give you a solution to the math battle, but since I went to the trouble of grading it, I have written a few solutions. So first order of business, I know some of you read that as 4x. I counted a little bit off, but anyway, so That was an x squared. That was actually a typo. I meant to put 4x there, which would have made this problem more interesting. But that is how I wrote, and it still makes sense. It's that. So a lot of you have not finished factoring. Like I saw many people leave it like this. This is not factored, my friends. This is a work in progress. That's the factored over the reals. And then a lot of people who did this nevertheless did that. So yay. So like you saw the more complicated one to factor, but the one that was like easier just kind of slipped past you. So there's that. Part D is not complicated actually. So you just complete the square on this thing. If this is a prime, it's either all positive or all negative. This one's all positive. And so it just is the same as x is greater than 0. Since this is always at least 1, the answer is 0 to infinity. So that was that. Now, that's just a brief college algebra review, right? This one here, I think a good number of groups got this right. Hooray. That gives me hope. I mean, but be careful. And also, I hope these solutions are correct, but if you find an error, let me know, all right? Because I did this, I haven't checked it with any reliable source. So it's possible I make an arithmetic mistake somewhere in these solutions. I mean, I try not to, but if you think you found something, say something, all right? And then this one, oh man, come on. Tangent cubed, I break into secant squared minus 1 times tangent, which then gives me a tangent integral and a secant tangent integral, which is a u equals secant substitution. And that is, that works out to the natural log of the secant. And again, if you write sine over cosine, make a u equals cosine substitution. It works out to that, I believe. So there's that one. So these ones are pretty like straight down the middle. Totally unsurprising to see this kind of thing on a Calc 2 test. And if this kind of thing is on a Calc 2 test, I don't expect it takes you 10 minutes. These are like 3-minute problems. Yeah. So anyway, this one works out to that. That can be simplified to like 1/3 minus 1/9 is 2/9, right? So yeah. So there's that one. Now I haven't done enough of this, I will say. If I have any criticism of my lectures and our interaction this semester is that I have been light on definite integrals, right? So when you have a definite integral, the integration by parts thing, you have to evaluate the uv, and this becomes before you actually did the integration, you'd have integral from 0 to 1, right? So when we have integration by parts with bounds, you have to mind the bounds. There are two paths, right? You could do integration by parts with bounds, or you could figure out the antiderivative and then apply the FTC2 to that. That's what I did here. I just did this in my head, wrote it down, and then used that. So so I will say this, like, if just something to watch out for yourself. So like I think on a math battle or two, I wrote like number. Answer should be number. Some of you have written like an expression plus a constant here for an answer, right? That can't be right. If you have a definite integral, then either it's an honest to goodness definite integral and the answer is a number, or it's an evil improper integral in disguise. And the answer is it diverges to infinity or does not exist or whatever. I mean, like, there are other possibilities, but it's never an expression, right? If you've got bounds, the answer is not an expression. It's either a number or a statement of non-existence of some type. This one here was not as hard as I'd hoped it to be. Because like I was hoping that you'd have to do like the adding angles. I was thinking you'd have to do adding angles identity, then you'd have like 2 integration by parts that looped separately. But my nefarious plan didn't work out, because you can just make a w substitution and then it becomes an integral of like, 2 cosine. There's a pi in here somewhere. And then you get w cosine w, which is of course integration by parts again, which gives you this and gives you that. I haven't cleaned up my answer, right? Because sine of square root of x plus pi is what? It's sine of square root of x cosine of pi times the cosine of square root of x times the sine of pi. So this just works out to minus sine root x. And this guy just works out to, I think, minus cosine root x. So like, these can be simplified. And this is manifestly not done, right? So like this solution is not as careful as my solutions for the mission, for example. Yep. Again, because in the interest of me sleeping. So this one here, I did something really different. So I'm sharing with you one of my tricks, one of my dirty tricks. which is that when you have an integral, right? So what's the whole point? What are we doing? What is integration about? It's about finding answers, finding functions whose derivatives, right, give you back the integrand. Everything we do is just a technique towards that goal, is it not? We're not, if you really get down to it, we're not deriving anything directly. Did you ever like write down the Riemann sum and actually work out the limit directly from the definition? I don't think you did, right? I only know how to do it for like a very small handful of examples. So usually integration is educated guessing, right? Now you've had an education, so make some guesses. This, I know what's going to happen. If I have 3 to the ax cosine bx, it's going to loop. You do integration by parts twice, it picks up a 3 a to the x sine x, and then you integrate by parts again, it gets you back to 3 a to the x cosine bx, yeah? And I know what's going to happen there. It's going to loop back. It's not going to be where it starts, right? Because I've worked this problem a couple times with you guys already this semester with different things, right? With e to the x, with sine, whatever. So I know that the pattern of the answer is a cosine bx plus b sine bx times that. Like that's what's going to happen. The real issue is, what are these numbers? The a and the b, that's all that's up for grabs. So what I do, differentiate the answer and set it equal to the integrand. And in so doing, it gives me 2 equations and 2 unknowns. There's an interesting trick to learn here, which is that when you have a sum of products of sines and cosines, the coefficients have to separately vanish. This is by the what's called linear independence of sine and cosine. They're distinct functions. You can't have them matching unless they have matching coefficients. And of course you can divide by 3 to the ax, because that's always non-zero, right? So divide by 3 to the x, that gets me this equation here. So I just equate the coefficients of cosine and sine. It gives me 2 equations, 2 unknowns, which I can then solve for these coefficients and then clean it up. Now, I think some of you got somewhat close to the answer here, but I don't, yeah.
Can you scroll up a little bit?
Sure.
Is the negative ab sine bx plus b cosine bx, is that an identity? Or
Derivative. So like I'm differentiating this, so I have a product rule. Derivative of 3 to the ax is a natural log of 3 to the ax, so that's the derivative of this term, times this unchanged, right? And then I have 3 to the ax here times the derivative of the thing in right here, which is the derivative of this is minus ab sine bx, because derivative of cosine is minus sine. Chain rule brings out the b. Over here, the derivative of cosine is cosine. Chain rule brings out the little b again. So that's that. So it's the product rule,
so
the chain rule.
Why'd you split it up from 3ax cosine bx to the 3ax?
Oh, this is from the left-hand side. I'm differentiating. Why did I write this?
Yeah.
That's my educated guess.
And why would you take the derivative of that?
Because I want the derivative of my answer to be equal to the integrand. That's the whole thing. What integration is find a function whose derivative gives you back the integrand.
Yes, sir.
So I know the thing is I know the format of the answer. So I can just fit the A and the B, yeah.
So for non-educated guess way of doing this, you just
Integrate by parts twice. It loops.
Pac-Mans and
Yeah, Pac-Mans. And you should eventually. Now, which is easier, integration by parts twice or my educated guessing method? I don't know. Teach his own.
yeah, I'm about to say.
So we're allowed to do this if we know, right?
Yeah, yeah. This is true.
You brave soul.
I would be able to.
You educated brave soul.
Now, others of you were perhaps lazier and tried to just bogart the formula from the the integral of like e to the ax times sine bx, which is in the notes, which is it's a noble move, but I think you'd need to like reformat that example. Like you could change a 3 to the x to an e to the x and maybe make that go. How would that look? How would you change 3 to the ax? Is ax? Yeah, 3 to the ax. How do I rewrite that as an exponential? I do e to the natural log of 3 to the ax. See, that's an identity, which is e to the a natural log of 3 times x. So if you're going to use my notes and try to steal my work for the math battle, and you're welcome to, you do need to adjust the problem so that it matches the problem in the notes. The way to do that would have been this. See, if you'd done that, then you could have looked at the notes and said, aha, well, I'm just replacing the constant that was given with a log 3, and then you could have directly lifted the formula from the notes. that would be the laziest way to do this. You know, sans Wolfram alpha, of course, but. As we know, you've been watching the chat GPT, you know that the computers are starting to get wise to us. Like the, you know, the, what's it called, the synchronicity or whatever, the computer's gaining consciousness. It's only a matter of time, so you got to prepare for them being evil. So we need to learn how to do math without the computers. It's part of it, you know. You got to prepare for the robot holocaust. You never know. So. What? I'm sorry, are you friends with robots or something? Oh, that's right. You are. You all are. So. Oh no, I'm part of the problem. I've got one of these. Let's see here. But it is a problem. No, okay, so here's a bigger problem. So I did this because I thought it would be healthy for you to integrate inverse hyperbolic cosine, right? So it's integration by parts. The integral of inverse hyperbolic cosine is integration by parts. Just like the integral of inverse sine, just like the integral of inverse cosine, just like the integral of inverse hyperbolic tangent. All right, so u, v, dv, I do my integration, I do my differentiation. Derivative of inverse hyperbolic cosine is 1 over theta squared minus 1 in this notation. And the theta is the v, so this is v du. All right, so da-da-da-da, integral. And then I went, okay, well, I'm going to now apply my initial condition. Integrate from 0 to t, right? I put tf because if I'm integrating over t, I don't want to use the same t. I could just use the same t. You guys wouldn't even be bothered by it, but I'm trying to be correct, all right? Anyway, so then I know the antiderivative, so I just use it, right? And then what happened? Then I was like, wait a second. This is what happens when I put t in. That's not too troublesome. But then I thought about putting times 0 in, and then I was looking at the square root of minus 1. At which point I was like, wait a minute. I can't give you the velocity is inverse hyperbolic cosine, and in the same breath tell you an initial condition at time 0. Why is that? Because the domain of inverse hyperbolic cosine is what? The range of cosh. What's the range of cosh? 1 to infinity. So it is unreasonable to give you an initial condition at time 0 for this function. How dare I, indeed? How dare I? So the good news is when I make a mistake like this, everybody gets full credit. So.
You should make a mistake in every test.
So the following question is, please put this question on the test. I know. Yes, yes, yes. Okay, very good. But all right, so there's that. These are the easier ones. That's an odd function. The integral of an odd function, 0. Done. Some of you worked much harder to not get that. This one here, cosh minus sinh is cosh of 3x plus sinh of minus 3x. But remember, at the very start of everything, e to the x is what? It's cosh x plus sinh x, right? So if I have cosh plus sinh, I can rewrite it as just exponential. And the minus 3x because it's, you know, oh man, that should be 3x. This is a mistake because this would give me cosh. This could be e to the minus 3x, but then it's downstairs. So to put it back upstairs, this should be a plus. So this is wrong at the moment. I probably won't have time to correct it today. Are we good? Do you understand what I'm saying?
Yep.
Yes, no? What I'm saying is cosh of 3x minus sinh of 3x is equal to cosh of 3x plus the sinh of minus 3x because sinh is odd. Then that is exactly the exponential of, and this is cosh of minus 3x because cosh is even. So that's the exponential of minus 3x because there's a general identity which is that cosh theta plus sinh theta by construction is e to the theta. But then the thing is, that's in the denominator, so when I put it back upstairs, it should flip the minus to a plus, and so sorry about that. And again, I think you guys were trying to do this in some kind of really different way, right? So I guess I'm just trying to urge you to, you know, engage in situational awareness. What's situational awareness? It's like recognizing that your professor is evil and he will test you on pre-calculus at times. And so that was such a problem. This is such a problem. See, because this is cosh of 3 log x, right? So that's the log of x cubed. So that's e to the log x cubed, e to the minus log x cubed, which we bring the minus in the power, that gives you log of x to the minus 3. So this is just x to the minus 3. This is just x cubed. And that integrates. Now there is somebody who saw past my subterfuge here. Like somebody saw past, you saw what I was doing, and you got this right. There's a group that got it right, but not many. The sinh cubed is a pretty standard problem, right? If you know how to do sine cubed, then you should definitely know how to do sine cubed, right? It's the same trick. We split off sine squared, convert the sine squared to cosine squared, in this case cosh squared, and then make a u substitution. But hey, a lot of you guys got this right, so I feel like you've done enough of that that you're there's hope.
Is sinh e to the x minus e to the negative? Is that the identity?
Yeah, I suppose it's good to know the definition. Sinh of x is 1/2. I think you said this. I lost my memory. What did you say? Is that what you said?
Yeah.
Yeah. That is what sinh is, but you know,
I just want to make sure.
we don't ever really make contact with that to do this problem, right?
Well, I was just saying because of B is cautious.
Oh, yes. Fair enough. If I put sinh here, it wouldn't change much. It would just put a, change that plus to a minus, right? Yeah. Good question. All right, so problem 8 is actually an elementary integral, but it's one you might not have remembered. The derivative of inverse hyperbolic sine is 1 over 1 plus x, 1 over square root of 1 over square root of 1 plus x squared. So this is just straight up elementary integral if you know that. Now, the other way to do this, of course, would be make a, I mean, there's 2 different ways you could go here. The other way you could go would be to make an x equals, I think x equals sinh phi substitution. You could do that, or you could make a x equals tangent theta substitution, I think, right? And if you did that, I think you get integral secant or something. I think it becomes integral secant, so you could do it that way, right? But this is the easiest way, okay?
2 over secant, which would just be this.
2 over secant. Well, this gives you a secant. It's square root of secant squared. But up here you get a secant squared from the derivative of tangent. So it's a secant squared over secant, which ends up giving you, I think, square root of 2 maybe? No. Anyway, there are other ways to do it, okay? So this one here, well, come on. You know this is from a certain person. Who's this from? It's, yeah, this is, exactly. You know the lion by its paw print, don't you? Let's see here. So, but although I did have a problem like this in the previous version, I looked at my math battle from years ago, and I had a very similar problem actually, but it was different, but this is a new one for me. And I like it because the integral is actually not that bad. If you make a secant squared substitution because you got a minus, then that works out to just, well, it just works out the integral d theta, which gives us this, which gives us that. And then when I do FTC2, I get this monstrosity, which is actually not too bad when you actually work it out. I did the last term first and the first term last, my bad. Anyway, when I sort through that limit, inverse secant of 1 is 0, I think. And see, what I'm doing here is, as t goes to 0 from the right, this goes to exponential of 0, which is 1. So that's that limit. The limit takes place right here. That's it. It's not especially exciting. The exponential of the log of 2 over 2, that's the exponential of the log of 2 to the 1/2 power, which is square root of 2. And so, I mean, it's, Dr. Sperano is just proud of the fact this works out to pi. Anyway, yeah.
You could just make a u sub on that, right?
A u substitution on this? Oh, I don't think so. But
Square root of u to the x minus 1.
but then what are you going to do with, if you let u equal e to the x minus 1, then what's
du is equal to e to the x minus 1 and the negative 1/2, which...
Oh, no, the du is e to the x dx in that case.
Because I did it that way and I got pi. I'm not...
Huh, funny. But you see that? I mean, like du would be this. If I did that.
No, you make u square root of e to the x minus 1.
U square root of that. All right, so then that would be 1 over 2 square root of e to the x minus 1 times e to the x dx.
And then 2du over e to the x is equal to dx over e to the x minus 1, and then u squared is equal to e to the x minus 1. U squared both sides. And then you get, after you substitute it, it's like, you pull the 2 out, and it's 2du over u squared plus 1. And you pull the other 2 out, and then you can use arc.
Hold on a second here. So that's let's see here. So you got 2d. I'm going to go back to here. 2dx over the square root of e to the x minus 1. Yeah. And so you're saying make that substitution?
Yes, sir.
So if I do that, I have so dx over the square root is 2 du over e to the x, I guess. So if I solve this, I can solve this for dx over the root, yeah? And if I do that, I get 2 du over e to the x, yeah?
And e to the x is equal to e to the x
So that gives,
u squared plus 1.
so that gives me this. You say e to the x is
Equal to u squared plus 1.
2 du over u squared plus 1. Cool, yeah. Yes, I will agree, yeah.
Look at you go.
Very good.
I want to be like you when I grow up.
Nice. That is another way to do this. I can see why you get pi too. Nice. All right, so let's see here. This one I don't have a solution of to show you, but it works out to that. If obviously, like, how would you do this problem? How would you do this problem? You got to do what? Partial fractions, right? You do partial fractions decomposition, like a over x plus b over x squared plus cx plus d over x squared plus 2, work it out. And then it ends up, these are the terms that come from that integration. So, see if I have anything else to show you from Math Battle. Here's the derivation of the inverse hyperbolic tangent formula if you wanted to see it. Here's the derivation of cosine squared from the imaginary exponential way of thinking. Here's the derivation of the cosine squared identity from the adding angles way of thinking. There's 2 different ways to do it. This one I probably should show you. Problem 14, I said, you know, how would you rewrite cosine of 3 theta as an algebraic function given that tangent theta is x plus 2? So what we do is we just convert cosine of 3 theta to cosines and sines of theta by appropriate application of the adding angles identity. So I do it like theta plus 2 theta, which gives me this, and then I can break these into the products of cosine and sine of just a single angle theta. And then I was trying to simplify it to something, I don't know, sometimes it's simplified nice. This is what I got to. You might be able to simplify it further, but there it is. That's an algebraic function, right? An algebraic function is just in terms of products and radicals and sums, differences, so forth, right? Basic algebraic operations. This is important, right? Because it is entirely likely that there's a problem on the test where I ask you to write your answer in terms of algebraic functions. So for full credit, you need to know this, how to do these kinds of things. Now, it's usually easier than this, right? Like, it's not always all that. Sometimes the issue is just like, if you make this substitution and your answer works out to, I don't know, sine theta, what do you put? You put opposite over hypotenuse, right? So if I had if I had sine theta, that would be equal to x plus 2 divided by the square root of x squared plus 4x plus 5 in this substitution. So that's the main idea that keeps coming up in examples that we've looked at. I think this one's just a plain old trig substitution, and here it is. I mean, I made a tangent substitution. It ends up giving me 1 over radical and a secant integral, which gives me this, and then, now this we could simplify further, right? Because you could factor out the 1 over square root of 2, and then you could absorb it into the constant, so you just had the log of the sum of the radical and x minus 1 if you wanted. So we saw that in an example in class, that kind of thing. I made a mistake. Problem 16 was not what I meant. Like, you don't need integration by parts to calculate the volume of a sphere, right? You did that in Calculus 1, a lot of you, right? Did you know integration by parts back, and you know partial fraction, excuse me. Did you know trig substitution back then? Search your heart. You know it's not true, right? Well, maybe it's true. It's true that you didn't know. I mean, maybe you did. I don't know you that well. You could have been studying Calculus 2 in secret before you took my class, for all I know. I don't know. But, so, anyway, if I do the method of disks, then the typical slice has volume pi x squared dy. When I integrate that thing, I get 4/3 pi r cubed. Not an integration technique in sight, right? It's not even U substitution. It's just straight up day 2 integration theory, right? Just linearity. I mean, yeah, there's the slicing the sphere up and setting up the volume integral. And then for shells, if you use shells on the sphere, well, shells gives you 4 pi x radical of x squared, r squared minus x squared. Again, yeah, I could do a trig substitution here, but by golly, I shouldn't, because that's a U substitution, right? I just let U equal the thing inside the radical. So again, the integral could be done with U substitution. So what I was thinking of, and I didn't connect the dots, was a circle. That's what I wanted to put down. How do you calculate the area of a circle? Well, you have to integrate, you know, so it goes from here to here, right? That's why there's a 2 times square root of r squared minus x squared. And to integrate that, we make a trig substitution of x equals to r sine theta. This one's interesting because I don't think we really had an example like this. How do you change bounds with a trig substitution? Maybe you haven't thought about this. It's in my notes, of course, but I think this example's in my notes. But if I have x equals to r, what does that force theta to be? Well, think about it. How can I get x equals to r? What theta do I have to make? I mean, I have to make sine theta 1, right? How do you get sine theta to be 1? You put pi over 2, right? And how do you get x equal to minus r? You need sine theta to be minus 1, right? That makes theta equal to minus pi over 2. So the reasoning there is a little bit indirect. And you're like, well, sine of theta is also 1 at like 5 pi over 2, right? Why not do that? Well, I think to be fair, we should pick a range of angles which is continuously assigned to the substitution, right? And so like minus pi over 2 to pi over 2 naturally corresponds to x going from minus r to r, right? So there's that. Anyway, so I change the bounds. I do my trig substitution, and you get integral of cosine squared. That's something we should be able to do on the test, right? If I put integral of cosine squared, nobody should get that wrong, right? That's an integral that we know how to do. Do we do it with integration by parts? No, not anymore. I did it once to show you it could be done, but by golly, don't do that. Do the 1 plus cosine 2 theta identity, right? And then we can integrate. 1 integrates to theta, cosine 2 theta integrates to 1/2 sine 2 theta, and then you got to evaluate from 0 to pi. Notice I traded my minus pi over 2 to pi over 2 integral for, I doubled it from 0 to pi over 2, right? That's a trick that's available to us when we're integrating something that's even. And of course, cosine squared is an even function of theta, so I can do that trick, which saves me some calculation. And anyway, surprisingly, or hopefully not, the area of a circle is pi r squared. But now, really, the tool you need to prove that is trig substitution. Yeah, so I think I buried the lead. I should have said that like 2 weeks ago, right? But anyway, any questions about the mission? I have posted the solutions. I have them here to look at. Anyone you want to talk about? We can talk about it. Yep.
I was doing work last night, and while I was doing those sine, not in secant to the fifth.
Uh-huh.
And I was using integration by parts, and it kept circling back, but I ended up getting like 0 over 2 because like my UV minus u2 v2 would equal 0.
Secant to the 5th theta d theta. It will loop, but it loops back to like integral of secant cubed, if I remember right. Is this a U substitution? I think secant to an odd power is not nice. It's not nice. But so I probably don't have enough time to work that out, honestly.
Because I looked it up online and they use some kind of reduction formula. That's the same thing as a recursive?
That's the recursive formula. I mean, that's, yes?
You can make it cosine of cosine to the 6th. Or cosine of cosine to the 6th. And then make the cosine of the 6th sine.
You said, oh, you said do cosine theta d theta over cosine to the 6th?
Yeah, and then make cosine to the 6th in terms of sine.
So you're like, I'll trade your problem for a 1 minus sine squared theta to the 3rd power, yes? So what we're really up against is du over 1 minus u squared cubed. And that's 1 over 1 plus u times 1 minus u, each to the power 3, which is, by the way, a over u plus 1 plus b over u plus 1 squared plus c over u plus 1 cubed plus d over u minus 1 plus e over u minus 1 squared plus f over u minus 1 cubed. So yeah, we could go down that path. Certainly. And it probably actually was pretty easy that way. I think that might be easier than the other path we're talking about. I don't know. Yeah. Listen, secant to the 5th is, like, I could give an integral involving secant to the 5th, and that might be the whole test. I mean, like, it's...
Let's do it.
Yeah.
I had a question that answered that in my mind.
I mean, I feel like integral of secant to the 5th is about a third of the test almost. Like, it's a long problem. Listen, I mean, so if I want to understand whether or not you can do integrals of secant, I can easily reduce it to secant cubed and learn about the same about your integration skill. Because secant cubed is more accessible. It's still hard, but it's not this level hard.
Do you have to use a recursive formula for that? Or
Again, I don't expect you to memorize the recursive formula, so if I want you to use recursive formula, like part A is going to be prove the recursive formula, and then part B is going to be apply it, you know? So, did you guys notice? I don't know if you noticed or not, but at the very end, you might not have got to this, but this is the Weierstrass substitution. And, oh, I guess I did put a different one on the, I thought maybe I'd put the same problem on the math battle as on here, but I guess I didn't. I had 1 over 2 plus cosine x in the math battle, but that was same as, like, that 1 over 2 plus cosine x problem is difficult, as far as I know. I mean, there may be some kind of trick like we did over on the board over there right now to do it, but so again, any particular question in the mission you'd like to talk about? We can. I did something funny here. You might be amused. So rather than accepting my fate of just doing the integral of e to the minus st times sine of bt, I used part A and assumed the complex calculation works. It does. See, this is the Laplace transform of 1 over 2i e to the ibt e to the minus ibt. But we already proved that the Laplace transform of an exponential is 1 over s minus a. So I just do that, but a equals to ib. And when you sort through the algebra, you get the right answer. That's because, by and large, complex calculations work just like real calculations. You just have to have the courage to sort through the I. That's all. In fact, you can actually, I've worked this out, you can actually, you can do trig substitutions. I shouldn't even tell you about this. No, I shouldn't even tell you.
Do it.
here for knowledge.
We're here for knowledge, yeah. So the, you know, if you have integral of like the square root of, oh, I don't know, x squared minus 1, you know, dx, how are you supposed to do that integral? A trig substitution, right? I mean, that's kind of like, that's all we know for that kind of pattern. So yeah, you're like, well, make an x equals what, secant? Secant theta? Then x squared minus 1 is, you know, secant squared theta minus 1, which is also known as tangent squared theta, right? So this is integral of square root of tangent squared theta. And then dx is what? Secant theta, tangent theta, yeah. So you got yourself an integral of secant theta times tangent squared theta d theta. Now that tangent squared you can trade for what? Secant squared theta minus 1, right? And so we're up against integral of secant cubed theta minus secant theta d theta, which we should be able to do, right? But I can't do it in 3 minutes.
Why wouldn't you split apart the tangent squared and then do a u substitution?
I did split apart the tangent squared, but a u substitution is not what awaits you. Secant times tangent, but the derivative of tangent secant squared, so it didn't help me.
Derivative of secant.
If I had secant squared tangent, it would be a different problem. Right? Secant squared tangent is easier, because that one you can re-image as just secant theta times the derivative of secant theta, because the derivative of secant theta is secant tangent. That's a u substitution. This is not. So here's the thing it was brought to my attention, is that you could just foolishly say, oh, I'm going to make x equals sine theta substitution. So that would be the square root of sine squared theta minus 1. Dx would be cosine theta d theta, right? Which is what? Integral of the square root of minus cosine squared theta, yeah? Because cosine squared theta, I mean sine squared theta minus 1 is minus cosine squared theta. So I times the integral of cosine squared theta d theta, which in fact is I over 2, integral of 1 plus cosine 2 theta d theta, and then that's like, you know, I over 2 theta plus 1/2. Now, yes, sir?
I'm kind of confused on where you got the, I know where you got the sine from, but where do you get the cosine outside of it? Is that just to cancel it out?
Oh, the x.
No, I'm not. Yeah, right there.
We have to change both the integrand and the measure. Dx is cosine theta d theta.
Oh, shoot. Sorry about that.
It's okay. I mean, so, see, but then the trouble is, that's not the answer. We want the what? We want the real answer, right? So, so in this case, sine is not real valued because you're, well, anyway, it's.
So you wouldn't accept that answer?
No, I would not accept that. I mean, no. Not until you sort through how to get rid of the I. There's another problem I worked where I was successful in getting rid of the I with this method, but anyway, yeah.
When you had the secant times tan squared, could you split that up into the sine, like in terms of sine and cosine, and you have sine squared over secant, sine squared over cosine,
You have sine over cosine cubed, yeah.
and then you could split
U equals cosine.
cosine cubed, or you could split cosine.
Oh, no, if you have sine over cosine cubed, just make a U equals cosine. No, there's just a sign here. This would be sine over cosine cubed.
Sine over cosine cubed.
Sine over cosine cubed, you just make a U equals cosine.
Why not be sine squared over cosine cubed?
Why would be sine squared? Which one are we talking about?
I'm talking about the tangent squared, you went straight from there.
Oh, tangent squared. Well,
cosine cubed.
Yeah.
Could you split the cosine cubed off to cosine squared plus cosine
Well-
cosine? And then sine it.
But that doesn't help, I don't think.
Does it not?
Well, you could make a partial fractions decomposition again, if you want. I mean, you can go. Well, no, it's just because you get a leftover cosine. I mean, it's. I don't think there's an easy way to get around the difficulty. Yep.
I know. I'm not gonna.
Well, guys, I think I'm out of time. Yep. See you at the test tomorrow.
Simply just. I just can't afford to waste time when I could be doing.
Someone stop the video. Can you hit the stop record button on there? It's